Hello everyone, and welcome to 7th grade Math Module 3, Expressions and Equations. In this lesson we're looking at lessons 19 and 20, Unknown Area Problems on the Coordinate Plane and Composite Area. Our learning goal is to make sure we can calculate the area of composite figures and of figures on the coordinate plane. This will help us to master Standard 7GB4, know the formulas for the area and circumference of a circle and use them to solve problems, and 7GB6, solve real-world and mathematical problems involving area, volume, and surface area of 2- and 3-dimensional objects composed of triangles, quadrilaterals, polygons, cubes, and right prisms. Before we get started, I have in the video a screenshot of our formula sheet that will be on the 7th grade Math PSSA. You can also find this in the Canvas course. So you will be needing to refer to a lot of these area formulas throughout this lesson. The coordinate plane below contains figure P and parallelogram ABCD. We're going to try to find the area of this parallelogram. We know from our formula sheet that the formula for the area of a parallelogram is the base of the parallelogram times its height. So the line BC or the line AD could be counted as our base. In order to calculate this, we need a number for one of those lines. So there are two strategies that we can use when we have this shape on the coordinate plane. We can either count along the coordinate plane to see how long the line is by how many jumps we have to make on the coordinate plane. Or we can find distance between the endpoints of the line segment using the points on one of the number line axes that makes up our coordinate plane. So I could count from, say, B to C or A to D to see how far apart they are, or I could look at my base BC and see that B is at 0 on the number line and C is at 5 on the number line if I'm looking at my x-axis, which my line runs along. Then I can use our distance formula of doing the absolute value of the difference of those numbers to find the distance on the line. Note that this formula only works when we're doing straight lines that run across a number line. If a line is diagonal like AB, we cannot use this strategy. So I can use either the counting or the absolute value of the two numbers to find the distance between these since they run along a number line. So our base is 5, but what is our height? Our height is not going to be the length of a line like AB, which is good because you guys won't be learning about how to find diagonal distance until you get to the Pythagorean theorem in 8th grade math. So what I need to find is the distance from AD to B, and that runs along the y-axis, so I can think of it as a distance on a y number line. So I know that my height starts at -4 on the y-axis at the bottom, and it goes all the way up to +2. So I can either count that distance on the number line, or I can find the absolute value of -4 minus 2. Whichever strategy I use, I find that the height is 6. So once I have that base and the height, all I need to do is multiply them together to find that the area of this parallelogram is 30 square units. Next, we have a slightly trickier problem on the coordinate plane because this one is a composite area problem. So we have to find the area of this shaded region, which is a sort of ring shape. And we're going to use 3.14 for pi. Well, this ring shape looks an awful lot like a circle, so we can use the area formula of a circle to get started. Looking at my circles, it seems like if I filled in the inside of this ring, I could have one large circle. It goes around this outside piece here. And then on the inside, I have a smaller circle where there's like a hole cut out, like the inside of a donut that's missing. So if I could find the area of the bigger circle that I would get from the outside and subtract away the area of the missing piece in the middle, that should leave me with the area of my ring. But we need some radii to do that. So first, you can pause the video here to try to find the radius of your big circle and then the radius of your small circle, either by counting or by subtracting your difference. So using one of those strategies, you should have seen that the distance from the center of the circle to the outside of the ring, which would be the radius of our big circle, is 3 units. If you use the same strategy for our small circle, the white piece on the inside that looks like it is missing from our ring, you would find that the radius is 2 units. So once you have those, you can plug them into our formulas for area of a circle. For the big circle, you would do pi times 3 squared, which gives us 9 pi. For the small ring, you end up with pi times 2 squared, which is 4 pi. Next, since I know I'm going to be subtracting those to find the volume of my ring, I can subtract them now before I even calculate with pi. And I can treat my pi like a variable, and my 9 and my 4 like coefficients. And since these would be like terms, I could do 9 pi minus 4 pi to find that the area of the ring is 5 pi. Then, when I use the 3.14 for pi on my calculator, I get that 5 times 3.14 gives us 15 7/10 square units for the area of our ring. Now we have one final composite area problem to try. This one looks like it might be simple, but can be deceptively tricky. We need to find the area of the shaded region, and again we can use 3 1400ths for pi. So looking at this problem, we see that there is a triangle, and we see that there's a semicircle. So we know that we can use the formula half base times height for our triangle, and the formula pi times radius squared for the circle, which we then have to divide by 2 for the area of a semicircle. Since these pieces are put together, we should put them together. You can pause the video now to try to solve those on your own. Be careful when looking for the height of your triangle. Let's review how to solve this by starting with the simplest part, which is the area of our semicircle. They gave us the radius in this problem of 4 centimeters. We know it's the radius because it's the distance from the diameter to the tip of the circle, and if I drag that over to the middle of the circle, it would go from the center point to the outside. So I just plug that into my formula, and I get pi times 4 squared divided by 2. Following PEMDAS, I have to use my exponent first, so I end up with pi 16 over 2 times pi, and then I can simplify that by doing 16 divided by 2 to get 8 pi. I can then use 3.14 to multiply by our 8 to find out that our area is about 25 1200ths square centimeters. So that's our semicircle. But what about the triangle? Well, the base is 14, they gave us that, but they didn't give us a number for the height. Looking at my height, I see that it forms the bottom piece of my semicircle that goes across the whole length of it. That makes it the diameter of my circle. Since we know that a diameter is twice the radius, that means that our height would have to be 8, twice the value of our radius of 4. So we have 1/2 times 14 times 8 to find the area of our triangle. When we calculate that in our calculator, we get 56 square centimeters. So now that we have the area of our triangle and our semicircle, we can then add those together and find that the area of this composite shape is 81 1200ths centimeters square. What does this make you wonder about finding the area of shapes on coordinate plane or finding the area of composite shapes? Write down your questions. Then you can look up your answers online or ask a classmate or teacher for help. Thanks for watching, and remember when you're trying this on your own, if you learn from your failures, then you succeeded.